All right, today we are diving into something, well, truly mind-bending in the world of material physics. We're going to explore a brand new way to predict one of the most fundamental questions out there for engineers. How and when do things break?
Okay, so let's start with a really basic question. How do engineers actually know when the stuff that makes up a bridge or an airplane wing or heck, even your phone case is going to bend or warp or just completely fail? It's a question that is, absolutely critical for pretty much everything we build.
Well, the answer lies in this concept called the yield surface. And the best way to think about it is like a 3D map, a map of a material's physical limits. Every single point on the surface of this map, that's a breaking point. So as long as the stress on that material stays inside the boundary, everything's cool. But the second you cross that line, that's it. The material changes forever. It either bends or it breaks. So understanding this map is it's everything. But actually creating it, well, that's the real challenge. And that's what we're digging into first, a material's breaking point. And right away, here's the problem in a nutshell. Mapping a material's limits with any real accuracy is, well, it's incredibly hard. You see, scientists often have just a few scattered data points to work with from their experiments. It's kind of like trying to draw a super detailed map of an entire mountain range when you've only ever seen a handful of the peaks, and only from a distance. This lack of data, this scarcity, it leads us straight to what's called the classic modeling problem. This really shows us how the old school methods have tried to solve this and, often failed. And this brings us to two huge pitfalls. On one side, you've got underfitting. This is where your model is just way too simple. It's like you're trying to draw a hexagon, but your model just gives you a circle. It totally misses the crucial details. Then, on the other side, you have overfitting. This is where your model tries way too hard to connect the few dots you have, and you end up with this bizarre, unnatural shape that has nothing to do with the actual physics of the material. The researchers behind this new AI model, they don't mince words. They put it bluntly, saying that these traditional methods are often just a form of glorified curve fitting. Ouch. But they have a point, right? They're just connecting dots, not really understanding the bigger picture. So if the old way is basically broken, what's the solution? This is where the hero of our story comes in. We're talking about a new kind of generative AI that doesn't just play connect the dots. No, this AI actually learns the fundamental physics of how materials behave. Okay, this whole workflow is seriously clever, so let's walk through it together. First up, the AI trains. It learns from a massive library of known material behaviors. Step 2, it learns to encode these super complex 3D shapes into simple 2D pictures called latent imagers. You can think of these as unique fingerprints for each material. Then third, it uses a generative AI technique called a diffusion model. And this is the cool part. It lets the AI take just a few new data points and generate a complete plausible 2D fingerprint from them. And finally, step 4, it decodes that new fingerprint back into a full high-resolution 3D model. It's an incredibly elegant process. And the scale of the training here is just immense. We're talking about an AI that learns from a dataset of 6,000 known yield surfaces, including all the classic models you see here. It's really like an artist studying thousands of portraits by the old masters before they even think about trying to paint their own from just a couple of reference points. And this right here, this is the AI magic at work. To learn how to build something, the model is actually trained to do the opposite, to reverse the process. It starts with a perfect, clean 2D image. Then it adds noise step by step until it's just static. And then it learns how to perfectly remove all that noise to get back to the original. By mastering this denoising process, it basically learns how to construct a perfect, physically realistic image from incomplete, messy information. This is really the heart of the whole generative model. And here is the incredible result. Look on the left, in image A. That's the sparse, incomplete data an engineer might actually have to work with. Then, in the middle, B. The AI uses all its training to generate this dense cloud of likely data points that are consistent with both the original data and all the physics it's learned. And finally, on the right, in C, that cloud is used to create a complete, smooth, and accurate yield surface. It's literally turning a rough sketch into a masterpiece. Okay, this is all fascinating, right? But what's the actual real-world payoff? Well, it all comes down to faster, more stable simulations. And this is where this model goes from being a cool idea to an absolute game changer for engineers. This side-by-side comparison, it tells the whole story. On the bottle, you can see how the old models really struggle with complex shapes. They become unstable or super expensive to compute. That's what all those red areas are showing you. But look at the AI model on top. It just handles these tricky cases smoothly, no problem. The simulation stays stable, which is what all that cool blue means. It's like having a self-driving car that doesn't get confused anymore by a complicated intersection.
So it's not just more stable, which is already a huge win. It's also dramatically faster. And in the world of high-performance computing and simulations, speed is everything.
So let's look at the hard data for a second. This chart shows the average time it takes to run a single step in a complex simulation. The classical model, over 11 seconds. The new AI model, just over 2 seconds. I mean, the difference is it's stark. So the bottom line is this. The new AI-powered method is over 5.5 times faster. And that's not some small incremental improvement, right? That is a massive leap in efficiency. It could unlock simulations that were just too time-consuming or expensive to even try before. So where is all this heading? Let's look at one final real-world test and then kind of zoom out to see what this really means for generating the future of materials themselves. Okay, so for this test, the AI was given just a few experimental data points for single crystal copper. Now, this is a notoriously complex material, but it's absolutely vital. It's in all of our electronics. And from that tiny amount of data, it generated a complete and physically accurate model of its behavior. This just proves the AI isn't just good with theoretical models. It works on real, cutting-edge materials that we use every day. What this really represents is a fundamental shift in how we do things. We're moving away from a world where we had to painstakingly measure everything to a new world where AI helps us intelligently discover things. AI can now help us understand a material's properties super fast from just a handful of data points. And that brings us to our final and maybe most provocative thought. What if this kind of AI could go one step further? I mean, what if it couldn't just model the materials we already know, but could help us discover and design entirely new ones? Materials with properties that right now we can only dream of. That's the truly exciting future that this research is opening up.